What if I told you that in the massive systems that run our world, time is basically a complete illusion? Today, we're going to dive into one of the biggest headaches in computer science. How do you make sense of time when every single clock is telling a different story? This is all about why our basic idea of what happened first just completely breaks down in distributed systems.
The great Leslie Lamport really just hit the nail on the head with this one. It perfectly captures this invisible, tangled web we're dealing with. See, it's not about just one computer. It's about tons of them, all trying to work together. And the one thing that's supposed to hold it all together is a shared sense of time. But, as we're about to see, that glue is, well, surprisingly weak.
So let's just cut right to it. In a distributed system, what you and I think of as time is fundamentally broken. It's a lie. If you're trying to figure out which database write happened first based on a simple timestamp, you're not just risking a little bug. You are building your entire house on a foundation of sand.
So let's start by unpacking that lie. Why can't we just trust the clock on a server? It sounds so simple, right? But the reality is, it's just fascinatingly flawed.
Okay, think about your own computer, running a single app. Life is easy. Events happen one after another. A, then B, then C. There's one single timeline. But in a distributed system, you've got multiple machines, and every single one has its own clock. There's no shared global clock, no single source of truth. Each machine is its own little island of time.
So, problem number one is something called clock drift. The little physical quartz crystal in your server that keeps time, it's not perfect. Because of tiny differences in how they're made, or even the server's temperature, one clock is always going to run just a little bit faster or slower than another. It's not by much, but believe me, over time it adds up.
And that drift, well, it leads directly to clock skew. That's the actual time difference you'd see if you could magically freeze time and compare two server clocks at the exact same moment. Because of drift, this skew is always changing, which makes timestamps from different computers totally unreliable for figuring out the order of events.
Now you might be sitting there thinking, hold on, don't we have NTP for this? And yeah, you're right, we do. The Network Time Protocol is designed to fix this whole mess. The idea is that servers check in with these super precise atomic clocks, figure out the network delay and the skew, and then correct the local time. Problem solved, right?
Well, not quite. And this is the critical flaw. NTP has to work over the network, and network lag is completely unpredictable. So an NTP adjustment might suddenly realize your clock is way too far ahead, and to fix it, it can literally make your server's clock jump backward in time. Just let that sink in. An event that happens later in the real world could get an earlier timestamp than something that already happened. Boom, your entire sequence of events is just shattered.
So, if we can't trust the wall clock time, what can we trust? The key here is we need a mental shift. We've got to stop thinking about seconds and minutes and start thinking about cause and effect. We have to capture the causal bond between events.
This brings us to a really simple but powerful idea, the happened before relationship. Think about it like this. If I send you an email, the act of me writing it had to happen before you read it. My action caused your action. That right there is a causal bond, and that is a truth we can build on, unlike physical time.
And that very idea is the foundation of Lamport clocks. They don't track seconds. They're just simple counters. Every process has its own counter that starts at 0. It ticks the counter up for any local event. When it sends a message, it sticks its counter value on there. And this is the key. When it receives a message, it updates its own counter to be the bigger of its own or the one it just got plus 1.
Okay, check this out. We can see that logic play out right here. Let's follow P2. It receives a message from P1, which has a timestamp of 2. At that moment, P2's own clock is still at 0, so it takes the max of its own clock, 0, and the incoming one, 2, which is 2, and then adds 1. Its clock instantly jumps to 3. This super simple rule guarantees that if event A caused event B, A's timestamp will always be less than B's. We've just captured causality.
But there's a catch, and it's a big one. Just because event A has a lower timestamp than B, it does not mean A caused B. They could be totally unrelated concurrent events that just happen to get those numbers. So with Lamport clocks, we can see potential causality, but we can't tell it apart from pure coincidence. So how do we solve that? How can we know for sure if two events are causally linked, or if they're just happening at the same time in their own little worlds? For that, we need a more powerful tool, the vector clock.
So instead of a single counter, a vector clock is an array,
or a vector, of counters. Each process now tracks not just its own time, but it keeps a counter for every single process in the entire system. It's like having a little scorecard for everyone.
The rules here kind of build on what we saw with Lamport clocks, but they apply to the whole array. First, a process increments its own counter in the vector whenever it does something. When it sends a message, it sends its entire vector, all its knowledge of the system. Then, when it gets a message, it merges the two vectors by taking the maximum value for each slot, updating its knowledge, and then it increments its own counting.
And this is where the magic happens. Look at that P2 receives event. Before this, P2's state was 0, 1, 0. It gets a message from P1 with the vector 2, 0, 0. So P2 merges them, takes the max of each element, which gives it 2, 1, 0. Then it increments its own counter, so its final state becomes 2, 2, 0. That vector is telling us that P2 knows about 2 events at P1, its own 2 events, and 0 events from P3. We're not just tracking a number anymore, we're tracking knowledge.
With this, we can finally get a definitive answer. Look at that top example. To compare vector A and B, we just check each position. Since every counter in A is less than or equal to its buddy in B, we know for a fact A happened before B. But now look at the bottom example, C and D. Neither vector is completely smaller than the other. This tells us they are concurrent. They happened in parallel, totally unaware of each other. We've just mathematically proven concurrency.
Now, of course, there's a catch. There's always a catch. Vector clocks are amazing, but their size grows 1-for-1 with the number of nodes in the system. That's fine for a handful of servers, but if you have thousands or millions of clients, that timestamp vector is going to get absolutely massive. It's a huge scalability problem.
Okay, so let's bring this all together. We started in this simple but totally false world of physical clocks, and we journeyed to this more complex but truthful world of logical time that's built on cause and effect.
This table pretty much sums it all up. Physical clocks, they measure wall clock time, but they drift and they jump around. Lamport clocks, they track that potential happen before relationship, but they can't prove it. And vector clocks, they can definitively tell you about causality and concurrency, but they have a scaling problem. Each one is a different tool for a different job.
So the most important thing, the big takeaway from all of this, is really a fundamental shift in how you think. In distributed systems, the right question isn't what time is it, the right question is what happened first. Causality, not chronology. That's the truth.
And that leaves us with one last really interesting question. Now that we can prove that some events are concurrent, that they happen in parallel without knowing about each other, how does a system break a tie? When two things happen at the same time, who wins? How does the system decide who's in charge? Well, we are going to tackle exactly that in our next explainer on leader election. You don't want to miss it.